lights over the board. Let's see what's on this pyramid. What's that? Okay, I'm glad you all found the room. I want to begin today by discussing these theorems, the two of them here. The first one I was telling you about at the end of the hour last time. It says that if you have two observables, I'll remind you that an observable is a complete Hermitian operator. If you have two observables A and B that possess, if you have them, then they possess a simultaneous eigenbasis if and only if they commute. Simultaneous eigenbasis means, first of all, a basis. Second of all, the basis vectors are eigenvectors. And third of all, they're eigenvectors of both A and B at the same time. I outlined the proof of this, the first part of this theorem, that if A and B commute and they possess a simultaneous eigenbasis at the end of the hour last time. The converse is that if they possess a simultaneous eigenbasis when they commute, and that's fairly easy, and it's discussed in the notes. So I won't go over it in class. I'll just remark that this is quite an important theorem in quantum mechanics, as we'll see as we go on. By the way, in matrix language, the equivalent of this first theorem is that if you have two Hermitian matrices, then they can be diagonalized by the same unitary transformation if and only if they commute. In that case, the unitary transformation takes you from some original basis you start with into a final one in which both matrices are diagonal. Well, that final basis is the one whose existence is guaranteed by this theorem. It's the simultaneous eigenbasis. In that case, the eigenvectors of the new basis are the vectors of the new basis are eigenvectors of both of the two matrices. Now, there's a special case of this theorem, which is part B here, which is really a trivial extension of it, but it happens so often and so useful in the course that I want to make particular mention of it. It says that if you have two observables A and B which commute, then any non-degenerate eigenstate of A is also an eigenstate of B. I'll just outline the proof of this for you. Let's suppose we've got A, and let's say that U is an eigenstate of A. I'm really thinking of the non-degenerate case here. Excuse me. I'm thinking of the discrete case here. So this is the discrete spectrum. So that U is actually a vector of a normalizing vector that belongs to Hilbert space. Now let's suppose that this is non-degenerate. And let's suppose that also we have another observable A which commutes with B. Then the statement is that if I take B and let it act on U, I get something that's proportional to U. That's to say that the same vector U is also an eigenvector of B. We'll prove this way. Let's let psi be equal to, just define it to be B acting on U. And if we do this, and let's let A act on psi, this is the same thing as AB acting on U, but that's the same thing as BA acting on U because A and B commute. Now the A is adjacent to U, so it brings out the eigenvalue A, lowercase a. But lowercase a is just a number, so we can move it left to the B. And the result is this becomes A multiplying B times U, which is the same thing as A multiplying psi. And the result of this is that psi is also an eigenvector of A with the same eigenvalue lowercase a as the original state U that we started with. Now what does that mean that U is an eigenvector of B? Well, psi is equal to BU. The reason is that we're assuming this is a non-degenerate eigenvalue, so the eigenspace corresponding to this eigenvalue lowercase a is one-dimensional. And therefore, any two vectors that lie in that space, which is to say any two eigenvectors of A with that eigenvalue, have to be proportional to one another. So B acting on U has to be proportional to U. Let's call the proportionality factor lowercase b, and thus you see that it's also an eigenstate of B. Notice that this argument doesn't tell you what the eigenvalue B is, it just tells you that it exists, that this is an eigenstate of B. To give you an example of this, let's suppose we have a Hamiltonian which commutes with parity. This is a typical example of this theorem which occurs in quantum mechanics. Such Hamiltonians are very common in practice. Now let's suppose I've got an H acting on some state n like this, and it gives me an initial eigenvalue En, which is non-degenerate. And the statement is that n is also an eigenstate of parity. The eigenvalues of parity are plus or minus 1, so it's got to be one of the two choices, plus or minus 1. As an example of this, you might think of the ordinary harmonic oscillator. Its eigenstates are non-degenerate because it's one-dimensional, and it also commutes with parity. And according to this theorem, all of the harmonic oscillator eigenstates are also eigenstates of parity. In fact, as you know, the even ones are even and the odd ones are odd. Now that fact doesn't follow from this theorem here. You'd have to work with the harmonic oscillator to figure out which ones are even or odd. But the fact that there are eigenstates of parity does follow from this. All right, so those are some simple theorems. Now, next I'd like to turn to the subject of projection operators. Projection operator, this is the definition. The projection operator, or it's also called a projector, is first of all an observable, so complete emission operator, such that its square is equal to itself. P squared is equal to P. An operator that satisfies this property is said to be idempotent. It just means that you raise it to a higher power, you always get the same thing as the first power. The way to visualize a projection operator is to think about the floor here like this. To think about light coming down from the sun straight overhead. And the projection is equivalent to the shadow of a vector. So if I have a vertical vector like this, it projects to a point, it gets annihilated, it just turns into 0. But if you have a horizontal vector, its shadow is equal to itself. So in this case, the projector applied to a vertical vector is 0, and the projector applied to a horizontal vector is the horizontal vector itself, like this. As you see, the vertical vector is an eigenvector of P with eigenvalue 0, because I can multiply by V here if I want, the answer is 0. And the horizontal vector has an eigenvalue of 1. In fact, it's easy to show that the eigenvalues of projectors are always 0 or 1, because, well, here capital P is the operator, but if I let lowercase p be the eigenvalue, then the eigenvalues have to satisfy the same algebraic equation as the operators. So P squared equals P, and this implies that P is either equal to 0 or 1. There's only two eigenvalues, and it's obviously a discrete spectrum. And so, in the case of a projection operator, there are only two eigenvalues, and therefore only two eigenspaces. And this means that the Hilbert space decomposes into the direct sum of the 0 space and the 1 space. In this shadow image here, the 1 space is the horizontal space, and the 0 space is the vertical space. The 1 space are the ones where the eigenvalue is 1, so the vector, nothing happens to the vector if you act P on it, and the 0 space is the one that gets annihilated. Anyway, this always holds for projection operators. Now, projection operators occur frequently, they occur always, as a matter of fact, in resolutions of the identity. Let's suppose we have an observable A, and for simplicity, let's suppose it has a discrete spectrum. So let's call its eigenstates n and r here, eigenvalues a, n, and r like this, where r is an index which is used to resolve degeneracies. That's to say, it specifies a basis in the eigenspace en for the eigenvalue a sub n, like this. So r here runs from 1 up to the dimension of the nth eigenspace, which we'll call en like this, degeneracy index. Then we know there's a resolute, and then the orthonormality relations, by the way, are the nr scalar product of n prime r prime, or delta nn prime, delta r prime, as I mentioned last hour. Now, the resolution of the identity in this case is that the identity operator is the sum on n and r of the outer product of nr with nr. It's something like this whenever you have a discrete spectrum. What we can do here is to define an operator, it's actually a projection operator, Pn, which is the sum on R of the outer product of nr and r. Here we're summing only on the degeneracy index and not also on n. So this depends on n. Now this is a projection operator onto the eigenspace En. Projects onto the eigenspace En. How do I know that? I know it because if I let this operator act on any vector that's orthogonal to the eigenspace En, I get 0 because all these vectors sigma lie in that space, and the various eigenspaces are orthogonal to one another. Likewise, if I allow this to act on a vector which is in this space, I just reproduce the vector because this is a resolution of the identity inside the eigenspace. In fact, if we take this Pn and just restrict it to the eigenspace En, it becomes the identity operator in that space. That's really what a projection operator is. In any case, that's the projector onto En. And the result is that this resolution of the identity here, if I separate the n and the r sums, let me write it this way, sum n and sum of r. The resolution of the identity becomes this, because 1 is equal to the sum of the eigenvalues of the original operator of the projectors on the different spaces. And this is actually a statement of the completeness of the operator written in terms of projector language. All right. Another interesting thing is the operator itself can be written in terms of its projectors and its eigenvalues. It looks like this. The operator A is the sum on n of An times Pn, which I think is fairly obvious if you think about it, because if you let A act on one of its own eigenvectors that lies in the space En, and the Pn doesn't do anything to it, and the result is it just gets multiplied by An. All the other vectors that are orthogonal that get annihilated by that Pn. And so this has the effect on the basis of eigenvectors that the right-hand side has the same effect on that basis as does the left-hand side. So the two sides are, in fact, equal operators. So in the case of the discrete spectrum, this is how you express both the identity operator and the original operator itself in terms of projectors onto the eigenspaces. Now, let me say something about the continuous spectrum. Here it might be easiest if we just concentrate on an example which we've used before, which is the case of the momentum operator, the P operator, or P hat as we were talking about it in wave mechanics. So I explained last time the eigenfunctions of this operator are plane waves, which don't belong to Hilbert space because they're not normalizable, and they do form a continuous basis. Now, let's suppose, so here's a momentum axis like this, and let's suppose we choose momentum value P here, and this, of course, corresponds to an eigenfunction, which is a given plane wave. Now, first question is, does it make sense to talk about the subspace, the eigenspace EP, corresponding to a single momentum value? And the answer is no, because the eigenfunction in this case is not a subspace of the Hilbert space, because the eigenfunction doesn't even belong to the Hilbert space. It's not normalizable. And so this actually has no meaning. On the other hand, it's possible to talk about an interval, let's say going from P0 to P1, like this. Let's call it interval I, and the momentum space taking us from P0 to P1. And then what one can talk about is a projector onto a projector corresponding to the interval. Let's call it Pi. And what is this projector? Well, in this momentum example, it's the integral of the momentum from P0 to P1, the bounds of the interval, of the outer product of P with itself. Notice that if these ranges were extended to infinity, you just get the identity operator. But since it's only a finite range of momenta, what you get is a projector onto a range of momenta. This kind of a projector should be familiar to you from electronics or signal analysis. If you're working in the time domain instead of in the space domain, the idea is that you can design a circuit, you call it a filter, which would take a signal and would reject all frequencies outside of a certain frequency range. Well, in the spatial domain, that's equivalent to momentum. And so the idea is you want to have an acceptance function, and what's the step function looks like this when it acts on some input signal. Well, in fact, this is what this. So, in fact, this what that circuit does to time-dependent signals is really as a projection operator. And something similar to that being applied in quantum mechanics is this projection operator here. We remove all momentum components that lie outside this interval. You can see it's a projection operator because once you're inside this interval, if you apply it twice, you get the same result all over again. It won't change anything if you filter it twice. So in a continuous spectrum, we do have projection operators corresponding with intervals, and we actually also have corresponding subspaces of the Hilbert space that correspond to intervals of the continuous spectrum. Let me tell you a little bit about what the resolution of the identity and the resolution of the operator is in the case of the continuous spectrum. In fact, I'll even do more than that. We'll do it in the case of the case of a mixed spectrum, where you have both discrete and continuous eigenvalues. This is the, as I mentioned last time, this is what you get in the case of a hydrogen atom. So let's suppose we've got A acting on NR. This is a discrete spectrum, this AN NR. So this is R runs from 1 up to the dimension of the eigenspace En. And this is the discrete part of the spectrum. And let's suppose we've got A acting on, let's call it AR. Brings out the value of A as AR. This is in the continuous spectrum. So that A here belongs to some interval belongs to some interval which represents the continuous spectrum. Furthermore, let's normalize these vectors in the following way. NR scalar product of n prime r prime is delta n prime delta r prime. This is the discrete normalization. And for the continuous normalization, we have AR A prime R prime is a Dirac delta function in the A's, A minus A prime, and a Kronecker delta in the R's. The R here, R stands for resolution. The R here is just an extra index which is introduced in order to resolve degeneracies if you have more than one linearly independent eigenfunction for a given value of the A's. This actually occurs in the hydrogen atom with positive energies where you had, I think I mentioned last time, the states can be written this way. ELN, so the positive energies E is continuous, but L and M are still discrete. These are essentially scattering wave functions in the hydrogen atom with given values of L and M, but positive energies. In any case, these are the orthogonality relations in the continuum. And then finally, we have the orthogonality relations connecting the continuum with the discrete, which is that those are zero, those are orthogonal states. So in hydrogen, the bound states are orthogonal to the unbound states. All right, this is a complete set of orthogonality relations. Then in this case, the resolution of the identity looks like this: is that 1 is a sum of n and r over the discrete state of the outer product nr and r, plus an integral over the range of the continuous eigenvalues of dA, and then a sum over r of ar outer product AR. Likewise, the operator A itself can be represented by such a decomposition. It's a sum on NR of AN times the outer product NR and R. We just simply multiply each of these terms by the corresponding eigenvalue. And then in the continuous spectrum, it's interval dA, and we multiply by A, and then we sum on R, AR, outer product AR, like this. All right. This last formula can be generalized to give us a representation not just of the operator A, but in fact a function of the operator A. If I want a function of the operator A, I just take a function of the eigenvalues. Just replace the eigenvalue by a function of the eigenvalues. What this means is if you have an operator A and you want to find a function of it, you just go to the eigenspaces, and on each eigenspace you just use the function you're interested in, or the eigenvalue. We'll see interesting functions about non-trivial functions of operators appear later on in the course, including things like delta of A minus A naught, even delta functions, which are kind of bizarre functions of operators. But in fact, these are meaningful if you use this representation of a function of an operator. Now, that's all I want to say about the mathematical formalism of quantum mechanics for now. And what I'd like to do now is to turn to the physical postulates of quantum mechanics, which allow us to connect the mathematical formalism with experimental results. We're actually not ready to present the physical postulates in the final form because we haven't talked about mixed states. So these are in incomplete form, I'll say in a minute well, in what sense they're incomplete. But here's what they are. These postulates, by the way, are the distillation of a tormented history of the development of concepts in quantum mechanics. These postulates took on their, more or less, this form already by the late 1920s. So they're not exactly recent, but the process of getting there was a very long and painful process. So they're not intended to be obvious, and in fact, they're certainly not obvious. But we're going to take them as given here as a starting point and see where they go. So the postulates run like this. First of all, the first postulate says that every physical system is associated with a certain Hilbert space, which I'll call script E. Hilbert space is a complex vector space with a scalar product on it. It has certain properties such as its dimension, and the dimension of the Hilbert space is actually determined by the physical system. I'll give you an illustration of that in just a moment of how we know that, how we know what the dimension is. Secondly, every pure state of the physical system corresponds to a ray in the Hilbert space. I haven't explained yet what a pure state is, and that's why these postulates are incomplete. I'll have to come back later and fill that in. So let's just leave that dangling for now. This is going to be incomplete from a logical standpoint, but you learn a lot anyway by going through this at this stage. Let me just say that a pure state, roughly speaking, is a state which corresponds to a wave function. That would give you an idea of what we mean by that. Array, I'll remind you, is a set of vectors in the Hilbert space which are proportional to one another. In other words, it's a one-dimensional subspace. This is usually represented by some non-zero ket which lies in the ray. The correct thing to say is the ray itself corresponds to the physical state, not any particular vector in the ray. Nevertheless, we're pretty sloppy about this in language. We frequently refer to a non-zero vector in the ray as the quote-unquote state, even though it's the ray that's the state and not the vector. This is because the normalization and phase of the state don't have any physical significance. So we just choose some conventional non-zero vector in there. Frequently we make psi normalized, but in most of this I'm going to assume that not necessarily that psi is normalized. The third postulate says that any measurement process you can carry out in the physical system corresponds to an observable, which is an operator that acts on the ket space. The observable means that it has of course, that it's a complete condition operator. Yes?
So is the correspondence always one-to-one? Is everything in the Hilbert space a physical state? Is every physical state element of the Hilbert space?
Yeah, if you're talking about pure states, yes. By state, you mean array, yes. If you mean vectors, then there's a set of equivalent vectors corresponding to the state. The measurement process corresponds to observables. Fourth postulate says that the results of the measurements are the eigenvalues of the observable. There's two possibilities. They could be discrete or they could be continuous. Discrete eigenvalues or continuous. Both possibilities exist depending on the measurement you're making. The fifth postulate says that the probability of measuring a discrete eigenvalue, call it A equals AN, or maybe I should say capital A equals AN, is given by the ratio, which is on the top, is the projection operator Pn onto the eigenspace corresponding to the eigenvalue which you measured, sandwiched between the state vector psi, divided by the norm of the state vector psi. Notice we're not requiring psi to be normalized, and in fact, this answer is independent of the phase and normalization of psi, which, as I say, they're non-physical anyway. In the continuous case, we can't talk about the probability of measuring an exact value for a continuous variable because that would be zero. We talk about the probability of measuring A on some interval, let's say A0 to A1. In fact, let's call it interval I like this, capital I. Then the probability is given by the expectation value of the projection operator onto that interval, again divided by the norm of psi. Finally, there's the last postulate, which is sometimes called the collapse postulate, which says that after the measurement, the state psi, the original state psi, is replaced by the psi, which the psi with the projection operator in the discrete case, replaced by the original state psi with a projection operator Pn, which projects onto the eigenspace of the eigenvalue which was observed. In other words, psi becomes an eigenstate now of the original operator A with eigenvalue of An. It becomes projected onto that eigenspace. Likewise, in the continuous case, if we've measured A lies in a continuous interval, then projection operator is the one that corresponds to the continuous interval. All right. So those are the postulates. Now, in their incomplete form. Now what I'd like to do is to illustrate these postulates in the case of the Stern-Gerlach experiment to show how these postulates can be connected in a real example. It isn't quite a real example. We'll be talking about the Gedanken experiments. There was a real Stern-Gerlach experiment which has been repeated many times, but certain variations of it have never been done as far as I know. So part of this is Gedanken experiments. But nevertheless, you can take the results that I quote as being experimental results. I don't think anybody doubts that they would be true. So let's go through the Stern-Gerlach experiment just using these postulates. Now, in this process, we play a certain game, which is we pretend we know nothing about quantum mechanics except these postulates. In particularly, yes?
So for the continuous spectrum, I mean, isn't the interval kind of arbitrary? We can make the interval as small as we want,
sure,
as long as it encloses A. So
sure.
in what way is this consistent to say that it changes to the P sub I of psi when P sub I is some arbitrary interval enclosing A?
I don't understand the question. The probability to make the measurement depends on the interval, because if you just think about a collimator that measures position of a beam, that's really what a PI is in that case. If you narrow the collimator, you're narrowing the interval. The probability goes down, of course, because you're reducing the number of particles you're accepting. Does that answer your question?
Well, I mean, you still get a certain answer A, right?
Yeah, no, you get an answer that lies inside the interval. The probability of having the answer lie inside the interval is given by this expectation, but you narrow the interval, the probability goes down.
Okay.
Yes?
So in the case of a degenerate, if you make a measurement corresponding to an eigen of a degenerate, if you get a degenerate eigenvalue,
Yes.
then does that uniquely take it to you get a unique state in the eigen subspace?
No. Yes, you get a unique state in the eigen subspace. However, if the eigen subspace is multidimensional, there's other states in that subspace that have the same eigenvalue. All right? Okay. So in other words, yeah. Okay. So I mean, if the eigenspace is multidimensional, we might get different output states depending on the input state, because if I'm projecting on the table, I have one vector here projects this way, another projects this way. They'd both be eigenvectors with a given eigenvalue, but they wouldn't be proportional to each other. They would not be the same state afterwards. On the other hand, if the eigenspace were one-dimensional, then all of these would represent the same state because they'd all be proportional to one another. Okay. All right. So I want to talk about the Stern-Gerlach. So as I was saying, in this, we're going to play a game here in which we pretend that we know nothing about the Schrodinger equation, wave functions, Pauli spin matrices, or any of that stuff. Stern and Gerlach didn't know about any of that stuff themselves. And here, the purpose is to understand how these postulates how they lead to an understanding of the spaces we're using. And unfortunately, I have to cover up the postulates in order to get a board I can write on. So, first let me say some things about the Stern-Gerlach experiment. The purpose of it, this was done in 1923. The purpose of it was to measure the magnetic moments of atoms. Magnetic moment, classical magnetic moment, is a vector mu like this. It's determined by any localized current distribution. And magnetic moments, so we could, in principle, you could measure magnetic moments of small dust particles with little iron bar magnets attached to them if you wanted to do it. They have definite magnetic moment vectors, and you can measure them. That was the idea of the experiment. Now, a magnetic moment, when it's measured by placing it in an inhomogeneous magnetic field. In a magnetic field, the magnetic moment acquires an energy which is minus mu dot B. And if you take minus the gradient of this in order to get a force, the two minus signs cancel and you get the force acting on it. So this is the force on a magnetic dipole. It requires non-zero force requires the magnetic field to have a spatial dependence mu is characteristic of the particle and doesn't depend on space, so the del operator really only acts on the beam. In the experiment of Stern and Gerlach, they used two magnetic poles that looked like this. One was at a sharp point and the other was flat, so there's a north pole and a south pole. The purpose of this is to create a strong magnetic field gradient near the pole tip of the North Pole here, because you need strong gradients in order to get a reasonable force. So the idea is that the apparatus would, this pole piece would go down like this, and so would the bottom one too, going across. And you run a beam through, and the beam would run, this goes some distance, you actually want to make this a meter or more. It's a fairly long magnet like this. And you have a beam that comes in like this, and you run the beam through here, like this, through the beam. This is an atomic beam of neutral atoms. The beam, by the way, they use the silver atoms. The beam, by the way, conceptually is created by having a, well, actually two. If you have a lump of silver in an oven, which would heat to a high temperature, they use silver atoms. Other atoms can be used too. So that you get some silver vapor in here. The silver vapor passes through a small hole in the oven, and from there it passes through a collimator to create a beam of silver atoms. All right. And then this beam is passed next to the magnetic pole. Now let's say that the z direction is the direction of the vertical direction in this diagram like this. Then along the axis of the upper magnet, the magnetic field is largely in the z direction, so that B is approximately equal to the magnitude of B times z hat. And thus this means that the force on the atom is given by mu sub z, the z component of the magnetic moment of the atom, multiplied times the gradient of the magnetic field, which itself is largely in the z direction. So the force is essentially in the z direction. Now, and so while the atom passes through this inhomogeneous magnetic field over a certain period of time, over that time, this force times the time gives us a momentum transfer. Momentum transfers in the vertical direction, so the beam will move, it will fan out in the vertical direction, like this, with an amount which is proportional to mu z, the z component of the magnetic moment, when it entered the beam. We can assume that if the original magnetic moment mu, and a reasonable assumption is the magnetic moment mu has a definite magnitude of the atom, has a definite magnitude, let's call it mu zero. And if so, the z component just ranges between plus and minus mu zero, depending on the random angle of orientation. And so what you would expect classically is you'd expect a continuous distribution of deposit of the final beam on the screen, ranging between a plus mu zero and a minus mu zero would be the two extremes. And you can figure out what mu zero is by looking at those extremes. Of course, what Stern and Gerlach found was something completely different. Instead of getting a continuous smear on their screen, they actually got two spots at plus and minus mu zero. And they were able to measure the value of mu zero, and it turned out to be in good agreement with the Bohr magneton that was actually known at that time. The ZH bar of the 2 over C, the numerical value came out to about right. All right. So this was the big surprise, and was regarded as one of the crazy aspects of quantum mechanics, that you should only have two spots here. It seems crazy because how can mu z have only two components, plus and minus mu zero? There's nothing special about the z direction. You can orient in the x or the y direction, and you get the same two spots. The classical vector can't possibly have just two different distributions of particles, can't possibly have just plus and minus components in all three directions. It makes no sense. So how do we interpret this? Okay, so let's try to do this from the standpoint of measurements of quantum mechanics. In the first place, let's take this beam from the oven and let's schematically indicate the Stern-Gerlach apparatus by measuring here, let's say, a component. I put a z here, but let's say we measure the component of x, mu(x) in the x direction first. And as I say, what comes out of this beam is two outcomes, which I'll just denote by plus and minus, but it stands for plus and minus the Bohr magneton for the values that are measured. And So what this means is if we look at the postulates of quantum mechanics, it tells us that mu x should be an observable or a complete emission operator acting on the Ket space of the system, which is the Ket space of the atoms. And since there are two outcomes, it means that there are two eigenvalues of the operator mu x, plus and minus mu 0. And therefore, the Hilbert space decomposes into two orthogonal subspaces corresponding to these two eigenvalues. Now, we don't know what the dimensionality is of those subspaces. That's to say, we don't know what the degeneracy is, but there's at least two subspaces, so the Hilbert space is at least two-dimensional. Also, we get the same two answers with the same mu naught, no matter how we orient the beam, x, y, or z. So, as far as making measurements of components of mu is concerned, there's no evidence that the Hilbert space has any more than two dimensions. The easiest way to proceed with this discussion is just to assume at this point that these two eigenspaces are in fact non-degenerate, so they're one-dimensional, and then later on come back to the question of degeneracies. So allow me to do that. Let's just make an assumption. Let's say the Hilbert space is two-dimensional. If that's so, then the eigenspaces corresponding to these plus and minus outcomes are both one-dimensional and both non-degenerate. Let's suppose in this experiment we take the minus outcome and we just throw that beam away, and we take the plus beam and carry it out to do further experiments on it. In accordance with the postulates of quantum mechanics, this is now represented by a one-dimensional subspace of the Hilbert space. Let's introduce a vector I'll call mu x with a plus sign. Mu x is the operator, plus is the eigenvalue. We'll take this to be a normalized vector which lies in this one-dimensional space. This does not specify the phase of this vector, which is still arbitrary. So this is not uniquely determined. We have to remember that. But let's just choose one vector in that space and call it mu x plus. Now, let's take this resulting beam and let's feed it into a second Stern-Gerlach apparatus, make this a tandem apparatus, feed it into mu y, where we measure mu y in a different direction. The experimental or Gedanken experimental results are that once again, we get two values, plus and minus mu 0, and they each come out with 50% probability. Same thing that actually happened in the first step, as a matter of fact. Excuse me, not mu y, let's make this mu z. Let's make this mu z. And so let's call the states by the, after you measure mu z, then according to the projection, or number 6, the last hypothesis, is after measuring mu z, the state is projected on the eigenstates of the operator mu z. And therefore, the state of the system in these two beams is represented by two vectors. Let's call them plus and minus. Here I'm using the notation that mu z plus or minus is just the same thing as plus or minus. I'll omit the mu z in the case of the z component, because we're going to take that as kind of a standard basis. But in any case, the statement is that the state of the system is now represented by either of these two states, depending which beam you look at, coming out, following the postulates. All right. Moreover, we take these to be normalized states. Now, as a result of this, we can take this mu x plus state. These two states now give us a basis on the entire Hilbert space. And so we can expand this as a linear combination of the mu z states like this with coefficients c plus and c minus. Also, and as I said, the probabilities here are 50% each. Also, the probability of measuring mu z equals plus mu 0, let's say, coming out the top side here, by our postulates, this is the state mu x plus, sandwiched around the projection operator p plus, like this. I don't need to divide by a denominator because we're assuming this was normalized, where the p plus is the projector onto the plus eigenstate of the mu z operator. So this probability becomes mu x plus scalar product of plus times the scalar product of plus of mu x plus, which is equal to the absolute value of mu x plus scalar product of plus squared. That's the same thing as the expansion coefficient c plus in this expansion, so this becomes C plus squared, which is experimentally equal to 1/2. And thus we conclude that C plus is equal to 1 over the square root of 2 times the phase, which I'll write as e to the I alpha 1, where alpha 1 is unknown at this point. Similarly, if I do this for the minus state, we find that C minus is equal to 1 over the square root of 2 times e to the I beta 1, where beta 1, or excuse me, alpha 1 beta, call it beta 1, where beta 1 is another unknown phase. So, by applying these postulates, we conclude that ux plus is 1 over the square root of 2 e to the I alpha 1 plus e to the I beta 1 minus this. All right. Now, allow me to, in effect, absorb this arbitrary phase into the phase convention of μx plus. I'll do this by writing this as μx plus with a prime on it times e to the I alpha 1. And then we'll multiply both sides by e to the minus I alpha 1. And what we get then is that μx plus prime is 1 over the square root of 2. But the space has been eliminated. Plus an e to the I beta 1 prime minus, where beta 1 prime is equal to beta 1 minus alpha 1. And now, if you allow me to do a dirty trick for lecturers, which is to use the eraser, I'm just going to erase the primes. And I'll put a check next to a μx plus. And what the check means is that we've now established a phase convention for this state. And we can't change its phases anymore. So with the phase convention for the μx plus state, we can write it as a linear combination of the eigenstates of mu z in this form. Now obviously we could have done something with the μx minus, the other being coming out of the first Stern-Gellner apparatus, and if we did, we could have gotten this, is that μx minus is equal to 1 over the square root of 2 plus, let's call it e to the I beta 2, minus like this, and I'll put a check next to that one because that means the phase convention for that state is also determined. Now, these phases can be nailed down further, however, because we know that μx plus must be orthogonal to μx minus, because these are vectors that belong to eigenspaces with distinct eigenvalues. In this case, of the operator μx. So this is equal to 0. And if you do a little bit of algebra here, what you find is that e to the I beta 2 is equal to minus e to the I beta 1. And so we can now combine these two statements together in this form to say that μx plus or minus is 1 over the square root of 2 times the state plus or minus e to the I beta 1 times the state minus like this. This is a condensed version of the two lines above, and you see now there's only one independent phase. And the phase conventions on the left side are determined. Similarly, instead of measuring μx first, we measured μy first, we did the same thing. We would obviously end up with similar conclusions. We'd get μy plus or minus. Could be represented this way as 1 over the square root of 2 times plus or minus a phase I'll call e to the I gamma 1 minus. And this would involve specifying phase conventions for the μy plus or minus states. So now there's two phases again. And what about the relation between them? Well, before I do those, let me point out that let me just say that at this point it's convenient to actually talk about the operators. Remember, an operator can be represented by a sum over the projectors onto the eigenspaces weighted by the eigenvalues. So, in particular, the operator μx itself, there's two eigenvalues plus and minus mu0. So it looks like this. It's equal to mu 0 times the outer product of mu x plus with itself minus the outer product of mu x minus with itself, like this, because plus mu 0 is that eigenvalue, minus mu 0 is that eigenvalue. And if you take this mu x plus expression down here and plug it into here and do the algebra, you'll find that mu x is equal to mu 0 times the following. It's e to the minus I beta 1 times the outer product of plus with minus plus e to the plus I beta 1 times the outer product of minus with plus. Similarly, for the mu y, you'll find that this is mu 0 times e to the minus I gamma 1 plus minus plus e to the I gamma 1 minus plus. And finally, mu z is the easiest bone write down. It's plus plus outer product minus 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 outer product. And here what I've done is I've written the three operators in terms of outer products of the eigenspace of the operator mu z, like this. And there's still these two unknown phases that occur here. All right. Now, we can proceed with these phases by imagining yet another tandem experiment. Instead of feeding mu z into mu x into mu z, they're going to feed a mu x into a mu y. And if you do that, again, you get two outcomes with probabilities of 50%. That means that a mu x, let's say the plus sign, is being fed into a mu y with either plus or minus sign. You can square that as a probability. The answer is 1/2. And if you take these states here, with a plus sign on the upper side and a plus or minus sign on the lower one, form their scalar product, set it equal to 1/2, do the algebra, this gives you a relationship between the phases beta 1 and gamma 1. In fact, what you find is e to the I gamma 1 is within a sign, a plus or minus sign, is plus or minus I times e to the I beta 1. So, again, if I may use my eraser, e to the I gamma 1 here I'll replace by plus I times e to the I beta 1. And the e to the minus I gamma 1, I'll make it minus I e to the I beta 1. And as far as this plus or minus sign here, which is not determined by this formula, we get a plus or minus out front. Y. And so by using these various combinations of tandem Stern-Gerlach experiments and making phase conventions, we can reduce these three operators to this form. Now, there's still this final unknown phase beta 1, and we've pinned down the phase conventions for the mu x and mu y plus and minus. We can't change the phase convention for the mu z plus state because it would mess up this equation. You see, it would have changed the alpha 1, which has already been absorbed. But we can change the phase convention for the z minus, mu z minus state. In fact, let's use it to absorb the e to the I beta 1. In other words, we'll say a minus prime is equal to e to the I beta 1 times a minus, like that. And if we do this, I'll again use my eraser, and it just makes the e to the I beta 1s go away everywhere. Like that. And now what you see appearing here is the three Pauling matrices. Because if I take the operator mu x and I write it in this plus or minus basis, it's mu 0, 1, 0, 1, 0, 1, 1, 0. The mu y is equal to plus or minus mu 0 times a 0 minus I 0. And the e to z is equal to mu 0 times 1, 0, 0 minus 1. One remark here is that there's still a remaining unknown sign. It's only a plus or a minus sign. It hasn't been determined by the postulates or the experimental data. But apart from that, you see the standard Pauling matrices appearing. The Y matrix is turning out to be purely imaginary, and the X matrix is purely real. We could have reversed that if we'd done a different phase convention for the Z minus state. If we put a factor of I in here, then the result would be that the X matrix would be real, and the X matrix would be imaginary, and the Y matrix would be real. So one of the morals of this is you can make one or the other of these two matrices real, and if you do, the remaining one has to be imaginary. This is, by the way, an indication of proof that in quantum mechanics it's necessary to use complex vector spaces with complex numbers. The postulates of quantum mechanics cannot be reconciled with the experimental results of Stern-Gerlach-type experiments using only real numbers. All right. Now, what about this final plus or minus sign? That's something that I will let you think about. So I won't. There's still a remaining unknown sign here, but we're pretty close to standard results. Okay. So this is an indication of how Hilbert spaces are constructed out of experimental data, how one knows what the operators are based on experimental results, and how one can use space conventions and other things to obtain standard representations for the operators. The quantum mechanics literature is just crawling with various space conventions that have been established over the years, and for practical calculations you have to know them and use them. But there's no physics in them, and the real physics is contained back in the postulates. All right. Now, allow me to return to the question about how do we know that these operators are non-degenerate. That was an important step here because it allowed us to use a two-dimensional Hilbert space. How do we know those eigenspaces of the mu x operator, for example, are really only one-dimensional? Well, the answer to this is connected with the concept of compatible or commuting observables. Let's consider an idealized measurement process in which we measure measure an observable A. So we've got some kind of an input state here. Let's call it psi 0 like this. And there's a whole bunch of outcomes that come out. These correspond to what's called the discrete eigenvalues of A. Let's say one of them is AN. And let's say all the others we throw away, and we take the AN state out here and call this resulting state after measuring the observable A on the initial state psi 0 and obtaining a value A sub n. Let's say the resulting state is psi 1. Well, according to our postulate, psi 1 is the projection operator corresponding to operator A with eigenvalue n applied to psi 0. Now, let's take this psi 1 and let's feed it into a second measurement of an observable. Let's call it B. This produces a bunch of outcomes. Let's say we throw all of them away except for one of them I'll call B sub m. And what comes out of here is another state we call psi 2, which according to the postulates of quantum mechanics, psi 2 must be equal to a projection operator onto the eigenspace of the operator B with eigenvalue B sub m. I'll call it PDM. Like this. This is acting on psi 1. And so this is the same thing as P sub Bm acting on P sub An acting on the original state psi 0 by the postulates of quantum mechanics. Now, let's look at the probability of measuring, let's say, first An, as we've indicated here, and then secondly B sub m on these two measurements. This is a conditional probability, the probability of getting B sub m given that we got A sub n in the first measurement. So it's the probability of getting AN in the first measurement, which is psi 0 sandwiched around PAN divided by the norm of psi 0 times the probability of getting B sub n given the first times the probability of B sub n with psi 1 coming in. So this is the probability of psi 1. This is the scalar product of psi 1, projection operator PBM psi 1 divided by the norm psi 1, denominator here. Now, this numerator up here can be written this way because psi 1 is PAN acting on psi 0. I'm doing something wrong there. Let's see there. Well, this is supposed to cancel with that, and it's not going to do it. Okay, I better stop. I'm a little over time anyway. I'll finish doing the rest of this next time. Hamiltonian, which commutes with parity. This is a typical example of this theorem which occurs in quantum mechanics. Such Hamiltonians are very common in practice. And let's suppose I've got an H acting on some state n like this, and gives me an initial eigenvalue En, which is non-degenerate. And the statement is that n is also an eigenstate of parity. The eigenvalues of parity are plus or minus 1, so it's got to be one of the two choices, plus or minus 1. As an example of this, you might think of the ordinary harmonic oscillator. Its eigenstates are non-degenerate because it's one-dimensional, and it also commutes with parity. And according to this theorem, all of the harmonic oscillator eigenstates are also eigenstates of parity. In fact, as you know, the even ones are even and the odd ones are odd. Now that fact doesn't follow from this theorem here. You'd have to work with the harmonic oscillator to figure out which ones are even or odd. But the fact that there are eigenstates of parity does follow from this. All right, so those are some simple theorems. Now, next I'd like to turn to the subject of projection operators. Brings out the eigenvalue a, lowercase a, but lowercase a is just a number, so we can move it left to the b, and the result is this becomes a multiplying b times u, which is the same thing as a multiplying psi. And the result of this is that psi is also an eigenvector of a, with the same eigenvalue lowercase a as the original state u that we started with. Now, why does that mean that u is an eigenvector of b? Well, psi is equal to bu. The reason is that we're assuming this is a non-degenerate eigenvalue, so the eigenspace corresponding to this eigenvalue lowercase a is one-dimensional. And therefore, any two vectors that lie in that space, which is to say any two eigenvectors of A with that eigenvalue, have to be proportional to one another. So B acting on U has to be proportional to U. Let's call the proportionality factor lowercase b, and thus you see that it's also an eigenstate of B. Notice that this argument doesn't tell you what the eigenvalue B is, it just tells you that it exists, that this is an eigenstate of B. To give you an example of this, let's suppose we have what I made is right, so the board was how's that? Okay, I'm glad you all found the room. I want to begin today by discussing these theorems, the two of them here. The first one I was telling you about at the end of the hour last time. It says that if you have two observables, I'll remind you that an observable is a complete Hermitian operator. If you have two observables A and B that possess, if you have them, then they possess a simultaneous eigenbasis if and only if they commute. Simultaneous eigenbasis means, first of all, a basis. Second of all, the basis vectors are eigenvectors. And third of all, they're eigenvectors of both A and B at the same time. I outlined the proof of this, the first part of this theorem, the mention of it. It says that if you have two observables A and B which commute, then any non-degenerate eigenstate of A is also an eigenstate of B. I'll just outline the proof of this for you. Let's suppose we've got A, and let's say that U is an eigenstate of A. I'm really thinking of the non-degenerate case here. Excuse me. I'm thinking of the discrete case here. So this is the discrete spectrum. So that U is actually a vector of a normalizing a vector that belongs to Hilbert space. Now let's suppose that this is non-degenerate. And let's suppose that also we have another observable A which commutes with B. Then the statement is that if I take B and let it act on U, I get something that's proportional to U. That's to say that U, the same vector U, is also an eigenvector of B. We'll prove this way. Let's let psi be equal to, just define it to be B acting on U. And if we do this, and let's let A act on psi, this is the same thing as AB acting on U. But that's the same thing as BA acting on U because A and B commute. Now the A is adjacent to the U, so if A and B commute and they possess a simultaneous eigenbasis at the end of the hour last time, the converse is that they possess a simultaneous eigenbasis when they commute, and that's fairly easy and it's discussed in the notes. So I won't go over it in class. I'll just remark that this is quite an important theorem in quantum mechanics, as we'll see as we go on. By the way, in matrix language, the equivalent of this first theorem is that if you have two remission matrices, then they can be diagonalized by the same unitary transformation if and only if they commute. In that case, the unitary transformation takes you from some original basis you start with into a final one in which both matrices are diagonal. Well, that final basis is the one whose existence is guaranteed by this theorem. It's the simultaneous eigenbasis. In that case, the eigenvectors of the new basis are the vectors of the new basis are eigenvectors of both of the two matrices. Now, there's a special case of this theorem, which is part B here, which is really a trivial extension of it, but it happens so often and so useful in the course that I want to make particular